Hello to all Catskill High Algebra students out there. Today we are doing more work on sequences. Today should be 5-6. All right, check your dates. Let's go and get started with recursive rules. They could say recursive formulas, definitions. It doesn't make a difference, it's the same thing. Recursive rules have their own rules. You have to tell us what the first term is for free, and then you have to tell us how to get more terms. Now this tells us what the first term is. A of 1 is 3, so you automatically just get to take that and put that on the line. A of 2, well, you got to figure that out. Well, at this point, n is 2 because we're on the second term. Place 2 in here. 2 subtract 1 is 1. So that brings you back to A of 1. So basically they're saying, consider the term before, which is 3, and add 5. That's 8. And it is a little quicker if you recognize this entire thing, an minus 1, as automatically being the term before. Which means every time you're trying to figure out a new term, you just need to know what the term before was, which is 8, and now you add 5, and you get 13. Term before is 13, and I add 5. 18. It's recursive, so we just keep doing it over and over. Term before is 18, and we add 5, we get 23, and that's how a recursive rule works. There's another one here, different notation. They use b sub, like a subscript, b sub 1, so the first term is 2. And then to figure out the second term, same thing. This b sub n minus 1 means the term before, or you can plug 2 in for n. So it looks like they would like us to multiply 3 times whatever the term was before it. Well, 3 times 2, 6. Now we work on this one. 3 times the term before it is 18. 3 times the term before it is 54. And 3 times the term before that is 162. And that's all there is to recursive formulas. The next type is called an explicit formula. They'd like you to give or they'd like you to write the terms given the explicit formula. So this is a little different, where you just take your n value, in this case n equals 1, and plug it in there. So if 1 goes in here, you'll end up 3 to the first, which is 3 times 1/3, and that calculates to be 1. And you just continually place 2 where n is, so 3 to the second is 3 squared, or 9 times 1/3 is 3. 3 in here, 3 to the third is 27 times 1/3 is 9. And you should notice a pattern here. It looks like multiplying by 3 every single time. Sorry, I had to get the cat out of the studio. And if it's true, 9 times 3 is 27, and we'll just check that real quick. Let's put n equals 4 in here. 3 to the fourth is 81 times 1/3. Yeah, sure enough, it's 27. So you notice that pattern of multiplying, multiply, multiply, and you multiply by 3 the same time on every term. And I think you guys talked about this yesterday as being geometric. Okay. Move on to part B. We're using different notation. You're just using the b sub, but the idea is the same. Place 1 in, and you end up getting 7 out. Place 2 in, and you end up getting 5 out. Place 3 in, and you end up getting 3 out. And you should see a pattern. It's not multiplying. It's like you're decreasing by 2. Subtract 2 maybe. Therefore, this last term would have to be a 1. So you could say I'm subtracting 2. And some people would argue, could I say I'm adding -2? Yeah, sure, same thing. And this right here, where you're adding or subtracting the same thing, is called arithmetic. Okay, and our next couple down here, we're going to actually try and write formulas. And before we write those formulas, I'm going to put up a graphic here. Hopefully it's useful to us. All right, so we should associate linear functions with arithmetic sequences. Linear functions use y equals mx plus b. We're quite good at that. We know that m is the rate of change. For sequences, we call that the common difference. What are we adding every single time? The b we call the zero term, or a term that exists before term number 1. So look at this very first one here, where you got 1 becomes a 6, 6 becomes 11, 11 becomes 16. It looks like you're adding plus 5, plus 5. So you can see what the common difference is. In this case, d is 5. I'm adding 5. Now what about the zero term? What's the term that would exist before this one? So just imagine, work in reverse. If you add 5 to go this way, you would have to do 1 subtract 5, which is negative 4. Okay, so that means you got the zero term as negative 4. You can write your equation. A of n equals 5n, and then you need the zero term, which is minus 4. So for an arithmetic sequence, adding or subtracting, that's all you need, and you have a sequence or an equation. All right, let me kind of get this graphic out of the way and proceed here. So same thing. We need to figure out how we're changing. What are we adding? All right, somebody would say, I'm not really adding, looks like I'm subtracting. Okay, that's fine. You can have a d value to be negative, negative 3, negative 3. So your difference is negative 3. All right, what would be a term that would exist as a zero term? Okay, think in reverse and add 3. So we're sitting at 31 there, and we're ready to write our equation. Let's use b and just use the subscript, b sub n. You don't have to, you can use a different letter. And so I put my d value, negative 3n, plus 31. And that's how we handle writing arithmetic formulas. That's it. Now, the next one has directions, and they tell us that this is geometric. Now, geometric, I'll get another graphic for you here. We should associate all geometrics with exponentials, okay? Which means that y equals ab to the x is very, very pertinent. And the a value is the term before, or the zero term. And the b is the multiplier, or common ratio. How are we multiplying to get to the next term? So let's try this. See if you see a pattern. What are you multiplying 3 by to get a 6? What are you multiplying 6 by to get a 12? So forth and so on. This is not a very tough one, so you might figure this out, that the r, or your multiplier, is 2. If you can't figure that out, there's always an easy way. You can always take term 2 divided by term 1 and get a quick multiplier. 6 divided by 3 equals 2. That's very helpful. All right, so we got the multiplier. What about the term before? All right, if the multiplier is 2 going this way, you would have to do the opposite. You would have to divide by 2. 3 divided by 2. Okay, that's all we need. So our formula, a of n, should be equal to 3 over 2, which is our zero term, in parentheses the multiplier, which is 2, and the exponent we'll use n. That's it. So if we know the multiplier in the term before, we've got the equation. All right, this question is a little tougher. Let's get rid of that graphic. To see the multiplier, You know, I'm not sure what I'm multiplying to make this happen. So I'm going to use this little trick up here. I'm going to take the second term, which is 81, and divide it by the first term, which is 243. And I'm going to just reduce that, and it becomes 1/3. And if you check it, this times 1/3, yep, this times 1/3, yep, this times 1/3. Okay, so we got the multiplier, we just need the term before. All right, so instead of multiplying by 1/3, you divide by 1/3, and you are going to get 729 as a term before. So here's our formula. A of n, term before, 729, multiplier is 1/3, exponent's n. That's it. All right, let's turn this over. Number 5. If the first two terms of an arithmetic sequence are 4 and 11, respectively, which means in that order, so it goes 4, 11, and it's arithmetic, which means you're guaranteed we're adding. Well, what did you add 4? Add to 4 to get to 11. Looks like you're adding 7. So plus 7 plus, well, then you could keep going. You could do this until you have 25 terms listed. Kind of takes forever. But if we just write a formula, like we just did, A of n, you say 7n, and we need the term before this, which is -3. Okay, so 7n, I'm going to say plus -3. You could say 7n minus. I'm going to put 25 in here. So A of 25, 7 times 25 plus -3. That's going to bring me to 172, choice 3. All right, number 6. The first two terms of a geometric, that means we're multiplying, okay, are 2, then 6. You could hopefully figure out you're multiplying by 3, so you could keep going until you have 10 terms listed. That's one way of doing it. Or you can actually write the formula and say, well, if I'm multiplying by 3 to go this way, to get the 0 term, I would divide by 3. So that's going to be 2/3. The multiplier is 3, exponent of n. And if you want to plug 10 in, this might take some calculating. 3 to the 10th power has to be done first. It's a pretty big number. Choice number 1, 39,366. All right, number 7 is about a recursive definition. And they want to know what the fourth term is. Okay. 1, 2, 3, 4. Remember, it's recursive. They give us the first term for free. 13. Done. Now, if f of n minus 1 means the term before, it looks like they would like us to double the term before and subtract 3. Okay. Double the term before is 26. Subtract 3. 23. Double it. 46. Subtract 3. 43. Double it. 86. Subtract 3. 83. And that brings us to choice 1. And that's all there is to that. And bottom of the page is a graphic. The first figure requires 3 lines, the second figure requires 5 lines, and the third figure requires 7 lines to draw. Assuming this pattern continues, how many lines will it take to draw the 30th figure? Well, you can draw all 30 figures. I don't have time for that, but you can notice that this is a pattern. Hopefully you notice that's plus 2. Plus 2. That means it's arithmetic, which means there's a formula for this. A of n, and that means I know the common difference is 2. D is 2, so I'm going to say 2n. And what about a term before 3 that would exist, the 0 term? All right, if you're adding 2 to go this way, subtract 2 to go to the 0 term. That's 1. So the formula is 2n plus 1, and I could use that to figure out the 30th term. So 2 times 30 plus 1. And that's just 61, which is choice 4. All right, that's all there is to that, everybody. Good luck on your homework. Make sure you use this to help you. All right, goodbye.